For today's lesson, we will be discussing section 5.5, so the image and preimage of a function. So one of these we have already seen before, namely the image. The image of a function is just the range of the function. Now the preimage is a different notion, which is what happens if we take a set in the codomain, in the set of outputs, and consider all the elements that map to it. And so we're going to be considering this notion, proving some results. In the text, this is considered a research project, and so it has some exposition, but a lot of the material in terms of theory is relegated to the exercises. And so what we will be doing as part of our lesson for today is doing the one theorem in the text, and then doing several exercises from this section, and then you'll also have some assignments in the homework that will continue this investigation of the properties of the image and preimage of a function. So let us go ahead and get started. So the first thing we're going to look at is the definition of the image. So suppose f is a function from a to b, and x is a subset of a. Then the image of x under the function f is the set f of x. And so notice the distinction here. We are writing f of capital X. So now we have f of a set. And so usually when we write f of something as f of an element. And so that's something that is going to be understood implicitly. If we have f of a set, we are automatically discussing the image of that function for that set. And so here's the definition. We have f of x is equal to f of x for all those x's in all those lowercase x's in the set x. In other words, that's the set of outputs in B, so B and B, such that there is some lowercase x in the set x, such that f of x is equal to B. Now, in our definition, we have that x is any subset of A. So if we look at the special case, when we have f of A, then this here is the collection of B's in B, such that there exists some x in A, f of x is equal to B. So in the special case, when x is the whole set A, we do have that f of A, the image of A under f, is exactly the range of f. And so that's our first definition. The second definition is the notion of an inverse image. And for the inverse image, we proceed similarly, except that now we are looking at the set of outputs. And so we're now looking at the set B. And we take a subset y of B, and we define the inverse image of y under the function f to be the set f inverse of y. And we define this as the set of those elements in the set A such that f of A is in y. And so there's a few pictures that we can use to have an intuitive guide for how these behave. And so these are the following pictorial pictures you want to keep in mind. So here's our visual aid. On the left hand side, we have our set A, we have our set B, and we're going to consider the image of f under x. So we're going to do this first. On the right hand side, we have an identical picture. The only difference is that we are going to consider the inverse image in the right hand side. And so here we have again a set A or set B, but now we have a subset of B, which we call y. And so let's first investigate the image. So now we are looking at some subset x sitting inside the set A. And now this is going to have, when we consider the image, we're looking at how every element in x maps onto B. And so then this is going to give us some subset of B, which we're going to denote by the notation as f of capital X. And so here's our f of capital X. And what this, by the definition, this has the property that if we were to choose any element inside of this subset, so let's go ahead and choose our element B. what this is telling us is that if b is in f of capital X, then to be in here is to say that there is some element, let's call it lowercase a, in the set X, such that f of a is equal to b. And so now this lowercase a is inside the subset capital X. And so we can go ahead and have this lowercase a, and that maps to b. However, this is not saying that a is the only element that maps to b. And so it is possible that we have some other element that is, say, over here. Let's go ahead and call this element d. It is possible that f of d maps to b. But that's okay, because when we talk about the image of X under F, all we are saying is that we know that every element in here has at least one element in the set X that maps to it. And so we are guaranteed the existence of some element inside the subset X. And that's what we deduce to say. But it's just good to be mindful that there may be more elements. And so I'll do an example of a concrete function, namely the y equals x squared function, where we can have a concrete example of this phenomena happening in just a moment. But now let us investigate the inverse image. So with the inverse image, we have the same picture, except that now we're concentrating on b, and we have a subset y of b. And now, when we talk about the inverse image of y under F, that's going to consist of those elements a and a, such that f of a is mapping to f of y. So, if we take f inverse of y, now this is going to be a subset. And it has the property that every element in here, so if we call this here lowercase a, then there is some x in here, so to be in there, so a and f inverse of y, by our definition, is to say that f of a is in y. And so then we have our corresponding f of a is in here. And so we're looking at the set where all the elements in f inverse of y map to f of a. So this is a visual aid for understanding image and inverse image. So now let's see let's see an example with a function that we are used to. So let's consider y equals x squared. So here we are considering the function going from the real numbers to the real numbers, defined by f of x equals x squared. And now, when we talk about image, we're looking for any subset of the domain of the function. So we have the real numbers here. So let us go ahead and consider the set, the interval 1, 2. So let's go ahead and take x to be the set 1, 2. Sitting inside the real numbers. So when we look at f of capital X, this is going to be those outputs corresponding to inputs from 1 to 2. So all of this region here. So we're looking at these outputs. So all the numbers on the y-axis, which is really corresponding to our set of outputs, the set from 1 through 4. And so we see from the picture that this is the set 1, 4. But now if we go back to our intuitive diagram that we just considered, I mentioned that just because we have something in f of capital X, which we called lowercase b, that doesn't mean necessarily that every element in f of capital X has only elements in capital X mapping to it. We could also have some d that is not in X. And we see that here. Because now we can see that f of negative 1 is in f of capital X, since f of negative 1 is equal to positive 1. But negative 1, of course, is not in our set X, since we're only looking at that interval from 1, 2. So next, let us consider the inverse image. And we are going to look at the inverse image with now looking at the set Y in our definition to be the set 1, 4. So we're going to choose Y to be 1, 4. And we want to look at the inverse image of 1, 4. And so by definition, this is the set of real numbers. And so definition. So the set of real numbers A such that f of A is in Y. So we're looking at now the set of real numbers A such that f of A lands us in the set 1, 4. In other words, we are looking for those inputs in the domain of the function that map to an output in the set 1, 4. But this gives us these two possibilities. So we're looking at these two regions, and so we're going to have the set negative 2, negative 1, and 1, 2. So we actually have that the inverse image in this example is a union. The set negative 2, negative 1, union 1, 2. And so now that is the inverse image in this example. The next thing we are going to do is, to motivate the next theorem, is look at what happens when we take intersections. And so one of the questions that we are going to investigate today is how are unions of sets, intersections of sets, set differences, how are these preserved when we take images and pre-images? So here's what I mean by that. If we took f of, and so we're going to take in the inputs, we are going to be taking negative 2, negative 1, and now we're going to be intersecting it with 1, 2. So of course this is going to be the empty set, since both of these sets have nothing in common. There's no elements that these sets share. And so we really are saying f of the empty set. Now, in this notation, since this here is since this is the empty set, we have that we can't choose any elements. And so f of the empty set is just going to be the empty set. And this is not equal to the intersection of the image of negative 2, negative 1 intersected with 1, 2. Because if we had taken the intersection of the corresponding images of both of these sets, we get back that both of these give us back 1, 4. And so we do get back that this here is just 1, 4. And so we do have that this here is a subset. And that's going to be the context of our next theorem. But what ends up happening is if the function were 1-to-1, we will actually have an equality. And so the fact that these are not equal is a consequence of x squared not being a 1-to-1 function. And so that's what the following theorem tells us. And so here we have a function from a to b. We have w and x are subsets of a. And now we're taking f of w intersect x, so the image of the intersection of w with x. And we want to show that that this is always a subset of f of w intersect f of x. And in the event that the function is one-to-one, then we actually get equality. And the example we just saw demonstrates that that one-to-one condition is necessary. Since if we don't have that they are one-to-one, we have examples like the one we just did, where we can take an intersection, get back the empty set, and consequently empty set here. Yet, if we instead took f of the first set, intersect f of the second set, we do get something that is non-empty. So now, we want to show this set containment. But to show this, we're going to have to break this into two cases, because it is possible, as we just saw in our example, that the intersection of w with x is empty. So, suppose w intersect x is empty. Then f of w intersect x is equal to f of the empty set, which is going to be equal to the empty set. But the empty set is a subset of any set. So in particular, we have that f of w intersect x, which is equal to the empty set, is a subset of f of w intersect f of x. So that takes care of the case when the intersection is empty. So now let us consider the case when the intersection is non-empty. So we're going to suppose that the intersection of w with x is non-empty. If it's non-empty, we can now choose an element inside of that intersection. So let's go ahead and call that element d. Let me correct that. We're going to choose an element in the image of fw intersect x. And so let's go ahead and choose a d in f of w intersect x. By definition, for d to be in here is to mean that there is some element, and so in w intersect x, so back in by the definition, such that that element maps to the given d that we have. And so now we have d is in here, so by definition, there is some element c in the intersection of w with x, such that f of c maps to d. But now, f of c is going to live in f of w, because c is in w intersect x. So now note that c in the intersection, c being in the intersection of w and x, implies that c, of course, is in w and c is in x, and so this is just by definition of intersection, and thus f of c is in f of w and f of c is in f of x. Hence, f of c, which is what we called d initially, so d equals f of c, is in the intersection of the image of f of w under f intersected with the image of x under f. And now this shows that f of w intersect x is a subset of f of w intersect f of x. And so that shows the set containment. So now, what we are going to do is assume that the function is one-to-one, and we want to prove the equality of sets. Since we have already proven that this containment here holds for any function f, all we have to do is show the reverse containment in the case when the function is one-to-one. So let us do that. So lastly, suppose f is one-to-one, and let d be an f of w intersect f of x. Now, this is telling us that d is both an f of w and f of capital X. So by definition, we have that there is a c in w and c prime in x, such that f of c is equal to d and f of c prime is equal to d. Thus, f of c is equal to f of c prime, but the function is one-to-one. And by the one-to-one property, having an equality of this form, f of c equals f of c prime tells us that c is equal to c prime. And so consequently, c is equal to c prime since f is one-to-one. So, c is in both w intersect x, since they're both the same element. And so now we have that f of w intersect f of x is a subset of w intersect x, and by the first part, we conclude that we actually do have equality. And so now that finishes it off for this proof. So we are done. And so this was the situation when the functions were, when we were looking at the image. What if we were to consider the same question, but in the context of the inverse image? And so that's the context of the next question, which is also part of the question, exercise 2 in 5.5. And so now we have f as a function from a to b, and we are looking at subsets y and z of b, and we want to know, is the inverse image of y intersects z equal to the inverse image of y intersect the inverse image of z? And then we also have union, set differences. And so before we solve this question, let us do an example. So we're going to do this in two ways. We're going to consider, once again, the parabola and investigate this understanding through that example. And then we are going to consider a pictorial argument for this question. And then based on that, we're going to have a conjecture whether these are true or false and then we're going to prove our conjectures. So here's our parabola. And so for this example, we're going to take y to be the set 1, 4, and our set z to be the set 0, 2. And so now we're thinking about these as subsets of the real numbers, but specifically corresponding to the set of outputs. So this set here on the real numbers. So the set of outputs, so we're viewing it in terms of the y-axis. And so what I want you to do now is to pause the video and compute each of these quantities for y and z and see what you get. So pause the video, and when you unpause, I will go ahead and have the computations for each of these, and then we can compare. So let us get started. So if we take the intersection of y with z, we're going to have the set 1, 2. If we take the set difference of y with z, then we have to remove 2 from the picture since 2 is contained in z, but then we're going to have parentheses 2, 4. If we look at the pre-image of y, pre-image is another word for inverse image, but if we look at the inverse image of y, what we are going to get back is the set -2, -1, union 1, 2, and that should be a bracket. Because the inverse image of y is all those elements that map to the outputs 1 through 4. But that's going to be everything between -2 and -1, including those endpoints. And similarly with 1, 2. And that's what we have listed here. If we look at the inverse image of z, now we're looking at what are those inputs that map to the outputs 0 all the way to 2. And that's going to correspond to all the inputs going from the negative square root of 2 to the positive square root of 2. And so we got this here. So with that, let's look at the inverse image of the intersection of y with z. So that's going to correspond to all those inputs that map to the outputs 1 through 2. So in other words, negative square root of 2 to -1, and 1 to square root of 2 positive. And so we're going to have -√2 to -1, union 1 to square root of 2. Let's look at this intersection. Well, now we have these listed here explicitly. If we intersect both of these sets, we end up getting that that is exactly this union of sets. And so we do have equality. If we look at the union, then we have y union z, which we have to be the set 0, 4. So we're looking at those outputs from 0 through 4, and we want to know what are those inputs that map to it. Well, everything between -2 and 2. And if instead we had taken the union of both of these sets, we end up getting that both of these sets are equal. The third question, part C, we're looking at the set difference now. The set difference is going to be parentheses 2, 4, close bracket. And so now we're looking at everything that maps from 2 to 4, but not including 2. And so we're going to have -2 to the negative square root of 2, and then square root of 2 to 2, but not including square root of 2. And so that's going to give us -2, negative square root of 2, parentheses, union, square root of 2, parentheses, and then all the way to 2, bracket. But now if we took the set difference of the inverse image of y with the inverse image of z, so if we took the set difference corresponding to these sets here, we see that that's exactly this set right here. So we do have equality. And so this example is leading us to conjecture that each of these statements are true. What about the last statement, so part D? Is this always true? Well, we can't simply use the y and z we started with originally because y is not a subset of z. So we're going to do a relabeling. We're going to continue to keep the same z, but now we're going to look at y to be the intersection 1, 2. So let's go ahead and do that. And so here we have it. We have y is a set 1, 2. Z is a set 0, 2. So of course, y is a subset of z. The inverse image of y is going to be negative root 2, comma negative 1, union 1, comma root 2. So what we had over here. And then the inverse image of z is the same as before, negative root 2, comma root 2. So this seems to be implying that D is true. But there's a caveat. What happens is, it turns out that this implication is true, but the reverse one is not. And the way to see this is that when we're looking at the pre-image, we have to ask, is there some other subset y, let's call it y prime, of B, such that we get back this exact same set? And the answer is yes, because we're looking at subsets of B. In our example, the real numbers. And the negative real numbers don't have any input mapping to them. So, if we took y prime to be the set consisting of the negative real numbers union 1, 2, so our original set y, then the inverse image of y prime is going to be the same as the inverse image of y, because there are no elements of our domain mapping to the negative real numbers. And so we're just going to end up with the same exact set. But now we have a problem, because what we end up getting is that negative infinity to 0, this is of course a much larger set. And this is not contained in our set Z, which is just the element from 0 to 2. And so now this fails. And so part D doesn't hold in general. And so this is a false statement. So what I'm going to do next is discuss a way of perceiving A and B through a picture, and then I leave it to you to also extend that picture to part C and D and try to reason what must happen for in terms of the picture to get these statements intuitively. So now let us consider the same argument but through a picture. So here we have our set A, we have our set B, we have y and z subsets, and let us first consider part A. So we have the inverse image of y intersect z, and we want to deduce that these two are equal. The inverse image of y intersect the inverse image of z. So here's y intersect z. If we took the inverse image of this region, that's going to give us some subset of A. And so let's go ahead and call this the inverse image of y intersect z. And now let us say that we had an element in here, some lowercase a. Well, now that lowercase a, by definition, maps to an element in here. And so we have some f of a in there. But now that f of a lives in both y and z. And now if we apply the definition of what it means to be in the inverse image of y, we have that this f of a, by definition, will give us an a that lives in here and an a that lives in there. And consequently, we do have that this a is in both the inverse image of y and the inverse image of z. And a similar argument works for unions. if we chose some element in the union, and so we can choose now our A to be in here, that will tell us that f of A, because now A is inside in this picture inside f inverse of y, f of A has to be in y. And so we have f of A is over here. And by definition, we will have that f of A, since it's in the union of y and z, then A has to be in the inverse image of y union z. And so you can do a similar deduction for part C. So let's go ahead and formally prove this. From the argument I gave earlier, part A is true by the definitions. So let us go ahead and do that. So observe, so actually let me just write it like this. The set equality holds since, and now we're going to go ahead, we're going to choose A to be in the inverse image of y intersect z, and now this is equivalent to f of A being in the intersection of y and z by definition. But then, by definition of inverse image, and by definition of intersection, we have f of A is in y, and f of A is in z. So once again, definition of intersection. But now, definition of inverse image once more tells us that A is in the inverse image of y and inverse image of z. And finally, definition of intersection tells us that A is in the intersection of y intersection inverse image of z. And so that takes care of part A. And so we get the equality in this case. I will do part B, and I leave it to you to do the argument for part C. Now for part B, the set equality holds since, once again, we have A is in the inverse image of y union z if and only if f of A is in y union z. So I'm going to omit the reasoning, but this is again by definition of inverse image. Then we have f of A is in y, or f of A is in z by definition of union. And next, by definition of inverse image, we have A is in the inverse image of y, and then or A is in the inverse image of z. And finally, we have A is in the inverse image of y union inverse image of z. And so we got our statement in this case. So the next question is the following. So we have a function from A to B. X is a subset of A. Will it always be true that the inverse image of x is equal to x? So pause the video and give this a try based on what we did with a parabola, the f of x equals x squared. Do you think that this will be true based on a few examples? So give this a try, unpause, and then we'll give it a try together. Alright, so we have our parabola. Let's take our capital X to be the set 1, 2. So when we look at the image of capital X, that's going to be the image of 1, 2, and that's going to give us the correspond to the output 1, 4. But now if we took the inverse image of f of x, now that is the inverse image of 1, 4. And so now we're looking at all those inputs that map to 1, 4. But we have already seen that that corresponds to -2, -1, and 1, 2, the union of that. So we have -2, -1, union 1, 2. And this is most definitely not equal to 1, 2. So we see that this statement is false. But what is true is that you do have that containment. And so what is a true statement is that that is true. So this is false. And as an exercise, show that this is true. And so now I leave it to you to verify that in generality. And so that finishes it off for today's lesson. In our next lesson, we're going to move towards chapter 8. And so this will begin our investigation of infinite sets.